All right, this is the follow-up because we ran out of memory there. This is the rest of the Chapter 7 physics problems. This is the second assignment, the second half of that, numbers 35, 36, and 41. So, in 36, we have a variable force, in number 35, we have a variable force given as F sub 0 times x over x sub 0 minus 1. Now, I'm going to distribute that f sub 0 because then it looks more like the equation for a line in y equals mx plus b form. And that's a little bit more helpful for us to see it that way. As they suggest that we do it by graphing and then also by integrating. So I'll do what they ask. We want to know how much work is done between position 0 and position 2 x sub 0. So I'm just going to plug those values in and we'll see what we get. So when I plug 0 in here, I get minus f sub 0. And when I plug in 2 x sub 0 for this, the x sub 0's cancel. I get 2 f sub 0's minus an f sub 0 and f sub 0. So it looks like it goes from here to here. It's a straight line, so it would cross exactly halfway through, and that means the total amount of work done is 0. Right? And I'll tell you what, I'll let you try to do the integrating. It's a little bit crazy because of the fact, like, this is the variable and the rest of these things are constants. But you can try that. It's not that hard to do. The setup would look like taking the integral from 0 to x sub 0 of this expression, remembering that those are constants. That's the only variable here. This is a constant. So the antiderivative would be so 0 over x sub 0 times x squared over 2, right? That's the part with the variable in it. And then the antiderivative of a constant is just a constant times the variable of choice. And you can plug those in. Remember, we're plugging it in for the x's. When you plug 0 in, you're just going to get 0. And that does, in fact, turn out to be 0 also. All right. Number 36, we have another one of these graphs. And this time, they've just given us the actual graph of force versus displacement. Remember, we saw a couple where it was acceleration here, and we just had to scale it up by a factor of the mass to turn it into net force. Under the influence of a force that varies with position as shown in this figure. So I think we just need to find the area here. It's from 10 newtons down to 0, then it's 0 for a little bit, and then it goes down to -5. So I think we have this. These are all 2 meter intervals. So that'd be 20, this would be 10, this is -5 if you do those areas, and the total would be 25 joules when you find that area. No sweat. Again, just like in calculus, when you see one of these piecewise, very geometric type of functions, it should tip you off that maybe, in fact, you should already, before you even start, think about doing area, right? You should be in that frame of mind, like, I bet I have to take the area here. You'd usually be right. Now, last one is, was it 41? So, in 41, we have a single force, and that's acting on a 3 kilogram particle, and it has a position function. Position as a function of time, 3t minus 4t squared plus t cubed. And we want to know the work done from time 0 to time 4 seconds. So let me point out here that we need to be careful. This is if you're thinking about an integral here, that is the wrong road to go down, because we know that work is in fact the integral from x1 to x2 of a force function. But notice that this is for positions, right? So I don't think there's two problems with trying to go this way with it. I'm not given from position to position, I'm given from time to time. You're like, well, you could plug those in here and find the positions, but then I think I'd have a really hard time trying to find the force as a function of x, as a function of position. I can take derivatives of this and get to acceleration and then multiply by mass, but that would give me force as a function of time, right? So I think that we need to be very careful here how we approach this. So with that in mind, I'm not going to use this approach, right? This is true, but it's not going to work for us here. So I'm going to scribble on it for a little while. Okay, that's enough. What I am going to use is that the net work done is equal to the change in kinetic energy. And I think I can get at that because I have a position function. So if position is equal to this, velocity is the derivative of that. So that would be that, and the velocity at time 4 seconds would be equal to 3 minus 32 plus 48, which is 19 meters per second. And the velocity at 0 seconds is 3. So the change in kinetic energy, that's 1/2 mass times velocity squared. I shouldn't put units in some places and not in others. That's really sloppy. Minus 1/2 mass times velocity squared. And oh, where's my calculator? I think that comes out to be something. Okay, fine. So 1.5 times 19 squared is the same as 20 minus 1 squared, which is 400 minus 40 plus 1, right? So that'd be 361 minus 9, which is equal to 1.5 times 352, right? And 1.5, that's like 1.5 of these, so half of that would be 176. And if I add those together, I get 528 joules. You can check the math there. I think that is probably right. So there you go. So the important thing to realize here is the different paths there are. You can approach this from the, I'm going to do an integral side over here, or if you know about velocities, you can approach it from here. How do you know which one? Well, if you have one of those functions, like some kind of force versus displacement function, that's talking to you over here, right? If you have a position function, position is a function of time, that's talking to you over here. That's saying, hey, we could find velocities there, right? So, and the fact that we had times given here, I think that's also speaking to us here. Okay.